Hello and welcome back to my Physics Online video lecture supplement series. In today's video, I wanted to continue my lecture on solids and fluids, and specifically what I wanted to look at is fluid statics. So before we get into fluid statics, I wanted to briefly define what counts as a fluid. Basically, anything which yields very easily to shear forces is going to count as a fluid. This would be things like liquids, gases, and plasmas. Recall from the previous part of this lecture that a shearing force is a force which tries to make an object slide across itself layer by layer. So if the substance has different layers which are easily able to slide across each other, then it counts as a fluid for our purposes. If it does not, then it is probably going to be a solid of some sort. So there are a number of common properties that fluids have. For one, if you submerge an object in a fluid, then the object is going to experience some pressure from the fluid, and this pressure actually will increase with the depth at which it is submerged. Furthermore, because objects tend to have some thickness, the pressure tends to increase with depth in such a way that the fluid will exert a net upward buoyant force on the object. And these properties are going to pertain both to a static fluid and a dynamic fluid, but specifically I want to look at static fluids today. That's fluids which are not in motion. So there's a number of applications to fluid statics in a variety of different fields. For example, why does a balloon float or sink? How does a hot air balloon work, for example? How do you navigate hot air balloons? For that matter, why do submarines work? How does a submarine work? How does a fish work? How is it that fish can float at some given level in water without really exerting any additional effort? This fish could be just floating there in the water without having to move any of its fins to maintain this level. Similarly, a submarine can rise and sink without needing to turn the propeller screws to actually drive the submarine. So how does all that work? So to begin this particular part of the lecture, we need to first define a concept which many of you are probably familiar with already, and that concept is density. So density is commonly defined as mass per unit volume. So this is density defined. And so of course the SI unit is usually kilograms per cubic meter, although grams per cubic centimeter is often used in, for example, fluid densities. In general, the conversion factor is 1 gram per cubic centimeter is 1,000 kilograms per cubic meter. This is because while there are 1,000 grams per kilogram, there are actually 1,000,000 cubic centimeters per cubic meter. A related concept is one which is very often covered in lab classes, which is the specific gravity, and that is, of course, the ratio of density of a subject to the density of water at 4 degrees C. At that temperature, water has a density of 1.00 grams per cubic centimeter. So since this specific gravity is a ratio, it can be taken as rho of substance divided by rho water. That means it's going to be a dimensionless quantity. By the way, before I continue, I should note that there are plenty of other uses of the word density. You can have a charge density, for example. You can have a population density. Density might even refer to distribution per unit area or distribution per unit length, as opposed to per unit volume. So here are a few common densities. So aluminum and ice, copper, brass, gold, uranium, bone, lead, these are your solids. Here are a few liquids. Here are a few gases. So these give the densities always in grams per cubic centimeter. Among other things, note that air has a density of about 1.29 times 10 to the minus 3 grams per cubic centimeter. That's the same as 1.29 kilograms per cubic meter. So gases tend to be quite a bit less dense than, say, liquids or solids. Pressure is a concept which we discussed a little bit in the previous lecture. It was a type of stress, and specifically it was the bulk stress that can be placed on an object. Stress, of course, is always a force per unit area, and so pressure is no exception to that. It is average force per unit area acting upon an object would give you the average pressure. The SI unit is the Pascal, which is equivalent to newtons per square meter. Of course, there's quite a few other units used in measuring pressures, in part because there have historically been quite a few different methods for measuring pressure. The US customary unit is basically the pound per square inch, sometimes abbreviated PSI. Historically, millimeters of mercury were used. Atmospheres is a useful way of measuring pressure because that is the standard pressure of the air around us at standard temperature at sea level. There's also the millibar, there's also the torr, and a number of others. Basically, though, what pressure is it is a force which is caused by fluid surrounding some object which is attempting to rush inward to the space occupied by the object. And so if you were to remove the object, in this case a person, then all this fluid that's surrounding him would sort of rush in to the hole that's left by the person being removed from the water. And pressure, therefore, always is going to act perpendicularly to the surface on which it's acting. So it is a sort of normal force per unit area, if you will, although by a fluid rather than a solid. And as it turns out, pressure is something which is going to vary with depth. So if you have fluid which is at rest for a period of time, then that fluid has to be in a condition of static equilibrium. And so what this means is that at any given point, all of the forces acting on the fluid must balance. So here is a little bit of fluid that is specifically highlighted within an entire glass of water or other fluid. And in order for this bit of fluid to be at rest, all the forces acting on it have to be equal. That means the force this way, the force this way, the force this way, the force this way, all must balance. You must have zero net force. And so, among other things, what that means is that the weight of a column of the fluid has to be balanced by having a greater amount of pressure acting upwards from the bottom than there is from the top acting downward. And so pressure differences is what allows a given bit of fluid to stay in one location. If the fluid's at equilibrium, then this bit of fluid has to stay here, this bit of fluid has to stay here. It can't fall, it can't rise. The only way for that to happen is that the weight of this column of fluid must be balanced by a net upward force. That net upward force is the pressure from below pushing upward being greater than the pressure from above pushing downward. And so it turns out also that pressure is constant at a given depth below the surface of a fluid. So how does pressure vary with depth? Well, specifically, if you have a unit of fluid, say in this smaller box that has a height h and a cross-sectional area A, then there is a volume A times h worth of water in here, or of other fluid. And so the weight of this box of fluid must be the volume times the density times the gravitational acceleration. In other words, weight is equal to mass times free fall acceleration, and the mass is given by the density times the volume, where the volume is the height times the area. So this is the expression for how much this cube of water must weigh, or a cube of other fluid must weigh. Well, if there is pressure above this cube, then that upward force that is below it must nullify that pressure as well. All right. The weight of a column is mg, that's h times a times rho times g. And pressure is always going to be force per unit area. So the force acting downward from pressure above must be P times A, or P0 times A. The force acting upward from below must balance out P0 plus the weight of this. And so what that means is that this force acting from below must be P0 times A plus the weight, which was rho AHG, all divided by A, the area. And so the A's end up canceling, the cross-sectional areas end up canceling out so long as we're dealing with a column and not, say, a cone. And what that gives us is that the pressure below this must be equal to whatever the pressure above it is plus the weight of this thing divided by the area. So that is this equation right here. P0, that's the pressure above, plus rho GH is effectively the weight of this cube divided by the area of the cube. So let's do a few little examples with that. First example is, what is the pressure difference between an object at the surface of water and an object which is 10 meters submerged? So what we're looking for is the pressure difference, which we could label as delta P. So delta P is the pressure difference. Delta P is always going to be pressure 2 minus pressure 1, where pressure 2 in this case is given right here. So this is location for pressure 2, and then this right here happens to be location of pressure 1. Now, pressure 2 is going to be, by definition, P0 plus rho GH2, where H is how deep into the water are we. P1, similarly, will be P0 plus rho GH1. So this difference in pressures is basically going to be P0 plus rho GH2 minus P0 plus rho GH1. So that is our change in pressure. Notice if we combine like terms that the P0s will cancel and you end up with rho G, because that's in both of these terms, times H2 minus H1. Or in other words, that the change in pressure should be rho times G times delta H, or the change in depth. Okay, so with that being said, our pressure difference in question is going to be given by this density, which is 1.00 gram per milliliter times 1 kilogram per 1,000 grams times 1 million milliliters per cubic meter times G times H. And so this basically means that our change in pressure is 1,000 kilograms per cubic meter times 9.80 meters per second squared times 10.0 meters. Now, the reason why I had to change this unit into meters cubed is because I have meters here and I have meters here. Those are both in terms of meters, and so in order to make this force per unit area, if I want the area to be per meter squared, then every unit here needs to be in terms of meters. And so this 9.8 meters per second squared times 1,000 kilograms. That gets me into newtons. So kilogram meter per second squared is newtons. Times a meter divided by meters cubed basically means newtons per meter squared. So the pressure difference here is 10,000 times 9.8, which is the same as 98,000 newtons per meter squared, or 98,000 pascals. All right, so we want to know how this compares to the case in which the object is submerged in salt water rather than in fresh water. Okay, so how does the pressure we found before compare to the pressure that would occur if we were in salt water instead? So recall again, the pressure we found before was 98,000 pascals for 10 meters below the surface in freshwater. And it's worth noting that this is roughly equivalent to 1 atmosphere of pressure. An atmosphere is just a little over 101,000 pascals. We put 98,000 pascals by going down 10 meters, so rough rule of thumb, for every 10 meters depth you gain in freshwater, you're adding about 1 atmosphere of pressure. So let's see how it is for saltwater. And in fact, saltwater is going to be even closer to this rule of thumb, because the change in pressure, again, is density times free fall acceleration times the change in depth. And so what we end up with is 1,030 kilograms per cubic meter. Again, this should be in kilograms per cubic meter, and this unit cc is the same thing as 1 cubic centimeter. In fact, cc stands for cubic centimeter. So 1,030 kilograms per cubic meter is the same as 1.03 grams per cubic centimeter. So we multiply that by 9.8 meters per second squared. We multiply that by the depth, which was 10 meters. And so what we end up getting is that for salt water, the increase in pressure is about 100,940. So we could say very roughly 101,000 pascals. So this is, of course, going to be a factor of 1.03 times greater than what we got for fresh water. A quicker way to calculate that would have been to say, because instead of getting the actual pressure, we wanted to know the comparison between the two pressures. And so change in pressure for the salt water versus change in pressure for the fresh water for the same height, H is same, or delta H is same, should be equal to the density of salt water divided by the density of fresh water. So that's the quicker way to calculate it. And then again, note that this right here is even more nearly 1 atmosphere per 10 meters depth. And here's one more example to just kind of tie this part into the previous part of this lecture, which is how deep can you go without any fancy suits or anything before the pressure starts to crush your bones. Now, this is a somewhat imperfect example, of course, because this is compressive strength, which ties into the longitudinal compression, whereas pressure is a three-dimensional compression. But if you think about it, a three-dimensional compression is really a longitudinal compression, but along 3 axes. So what we need is we're trying to figure out when does the stress equal the maximum stress. And this stress right here is going to be roughly equal to the pressure, where P naught is 1 atmosphere, which is approximately 101,000 pascals. This unit right here says that P max is 1.5 times 10 to the 8. Newton per meter squared, or if you'd rather, that's 1.5 times 10 to the 8 pascals is the equivalent unit. So P is going to be P naught plus rho G H. And so what we're looking for is this one right here, given that P is basically going to be the max stress. So this means that rho times G times H plus the pressure at the top of the water is going to be equal to the maximum stress. Now, I didn't really specify what kind of water we're talking about, but presumably, since we're diving this deep, it's ocean, so salt water. So we'll use rho is approximately 1.03 grams per milliliter, which is 1,030 kilograms per cubic meter. Okay, this equation right here solves to get that height should be difference between this maximum and the initial pressure divided by the density times the free fall acceleration. And so this means that the depth that we're allowed to go to looks like 1.5 times 10 to the 8 pascals minus 1.01 times 10 to the 5th pascals divided by 1,030 kilogram per meter cubed times 9.8 meters per second squared. So what this means is that the maximum depth to which you can dive, about 14,850 meters. Now, with that said, this is how deep a person can safely dive in the sense of his bones are not going to be crushed into fine powder. Long before then, other deleterious effects begin to occur. So, this is approximately 15,000 kilometers or a little under 10,000 miles. 15,000 meters or a little under 10 miles. But long before your bones start to be ground into a powder, bones are going to break, lungs are going to get crushed, that kind of thing. So I wouldn't ever recommend diving so deep on the basis of this one calculation. There's a lot more that goes into dive safety than just this. All right, so this brings us to Archimedes' Principle. And what Archimedes' Principle states is that if you submerge an object in a fluid, be it totally or partially immersed, it's going to displace some fluid. And that displaced fluid is going to result in an upward buoyant force which acts upon the object. And that buoyant force is caused by a difference in the pressure between the top of the object and the bottom of the object. And specifically, you can look at it as the amount of buoyant force is going to be equal to the weight of the fluid which has been displaced. Now, the story behind all this, of course, is that Archimedes was a well-known scientist of his day, at least well-known within his city-state and maybe famed beyond there. And he was friends with, or acquainted with, and maybe later became friends with, the king of his city-state, which was Syracuse. And that king, at some point, was given a nice gold crown, or believed it was a gold crown. Perhaps he had supplied the gold to make the crown, perhaps it was a gift. In any case, the legend goes that he wanted to know whether the jeweler was entirely honest in making it. The jeweler could, for example, have melted gold and lead together and then fashion the crown out of gold plus lead. And it would still feel quite heavy, and crowns are very irregularly shaped, so it would be very difficult to actually measure the volume and hence the density of a crown. And the story goes that the king asked Archimedes to determine for him whether the crown was actually solid gold or whether it was using lead or some other heavy metal to act like a fake gold. And so Archimedes apparently went home and got into his bath, or maybe went to the public baths given that day, and got into the bath and saw a bunch of water overflow from the tub as he got in, and then he jumped out of the tub shouting "Eureka!" because he now had a solution for how to figure out the volume and hence the density of the crown. And then eventually he built this principle off of that. So here is a basic free body diagram of what happens if you place an object into a fluid. So the object has some weight, there's some buoyant force. The object's weight may be more or it may be less than the buoyant force, and that's going to determine whether the object will float or whether it will sink. And one way of looking at this is that if the fluid is all in equilibrium, if you were to remove the object, then that space that the object is occupying would be filled with fluid. That fluid would have a weight which is given by the volume of the object times the density of the fluid. And the fluid around it would need to be supplying a net upward force to hold this displaced fluid in place. This fluid that was displaced by the object is being held in place by the fluid surrounding it. So if you put an object there, it shouldn't have any effect on the fluid which is surrounding the object, and thus there should continue to be an upward force, which is the buoyant force, which acts upon the object. Now, a more thorough explanation might be given by a diagram more like this, in which we see that the top of the object is at a lesser depth than the bottom of the object, and that means that the force is sort of, or the pressure is sort of increasing as we go towards the bottom of the object and then decreases as we go to the top. And the result is that there's a net upward force due to this pressure difference. Either way, what we ended up getting is that the buoyant force is equal to the weight of the displaced fluid. And so you can write that the buoyant force is mass of the displaced fluid times free fall acceleration, which is the same as the density of the fluid times the volume of the object times the free fall acceleration. So you can also use this to determine whether an object should float or whether it should sink. Obviously, this is suggesting that if the object is more dense than the fluid, then it should sink, because that means that the mass of the fluid displaced is less than the mass of the object, and hence the weight of the fluid displaced is less than the buoyant force from this fluid surrounding it, hence it will sink. And if, on the other hand, the object is is less dense than the fluid, then the result is that there's more fluid mass displaced than there is mass of object to do the displacing, and so the buoyant force will exceed the weight of the object and it should float. Let's look at a quick example of Archimedes' principle and of the use of buoyant force and fluid displaced by determining what percentage of an iceberg is visible when the iceberg is floating in both fresh water and in salt water. All right, so what's the principle that we're going to use here? Well, what we need is for the weight of the iceberg to be equal to the weight of the displaced fluid, because that means that the buoyant force acting upward on the iceberg should be equal to the iceberg's actual weight. And so a free body diagram would basically look something like this. You'd have weight of ice, and you'd have the buoyant force acting upward, and this would be equal to the weight of the ice, and therefore you'd have a net force of 0 acting upon the iceberg, and hence it's at equilibrium floating. So how do you get the weight of the iceberg? Well, the weight of the iceberg is going to be the mass times the free fall acceleration, and so that's going to be the volume of the ice times the density of the ice times the free fall acceleration. And the weight of the fluid displaced should be given by, similarly, the mass of the fluid displaced times g, and so that should be the volume of the fluid displaced times the density of the fluid times g. And note that this volume right here should also be equal to the submerged portion of the ice cube's volume. So since this and this are equal, we should be able to write that the volume of the ice cube times the density of the ice cube times g is equal to the submerged volume times the density of the fluid times g. So what we're looking for here is, again, how much of the iceberg is visible. And this right here could be taken as being the difference between 100% of the iceberg and the part that's submerged. So we can write this quantity as 1 minus the volume of the submerged part divided by the total ice part. So this is basically equivalent to the fractional submerged portion of the ice cube. This whole quantity, therefore, is the fractional visible part of the ice cube. So ultimately, we're solving, therefore, for submerged over total. And you can see down here that volume submerged by the total volume, you can get by dividing both sides by this total volume, and then divide by rho times g. So you get the density of the ice divided by the density of the fluid displaced times g, or times g, and this one times g, I mean. And so in general, what this means is that the volume of the object, which is submerged, over the total volume should be the density of the object divided by the density of the fluid. So this is a true principle in general. Again, this is a consequence of buoyant forces, which is a consequence of Archimedes' principle. So the more fundamental principle here is knowing how the buoyant force works and knowing how Newton's first law works. The consequence is this equation. Okay, so this is telling us that for fresh water, we should have V submerged over V ice is equal to rho of ice over rho of fresh water. And so that's 0.917 grams per centimeter cubed divided by 1.00 grams per cubic centimeter, which is the same as centimeter cubed. And so if we wanted to get the percent visible, we'd do 1 minus, since this thing is already found, 1 minus 0.917, which is 0.083. So in other words, 8.3% is visible and 91.7% is invisible. This is for fresh water. for salt water, which is usually the actual case because these are floating in the ocean, not on a river. But in salt water, you would end up with V sub over V ice is equal to 0.917 grams per cubic centimeter divided by 1.025 grams per cubic centimeter. And the result of that is about 89.46% or 0.8946. And so 1 minus that, 1 minus 0.8946 gives us just a little over 10%. And so that would be 0.10, let's call it 0.105 because we don't really have so many significant figures. We only really have 3 significant figures. So about 10.5% of the iceberg is above water in salt water, and about 8.3% is above water in fresh water. This certainly gives some context to the old expression, just the tip of the iceberg. I wanted to look at now an active figure which has been put together by the folks at Cengage, which illustrates the point that I made in that previous example about being able to determine which percentage of the object is going to be submerged based on the density of the object and the density of the fluid. So generally speaking, if you have a floating object, it's going to displace its own mass and really more importantly, its own weight in the fluid. And if you have an object which is totally submerged, it's sinking or sunk, then it's going to displace its own volume worth of fluid. But let's look at an active figure in which we can change both the density of the fluid and the density of the object and see what percentage gets submerged. So we'll go ahead and start with both numbers totally maximized. Maximum density fluid, maximum density block for this active figure. And so of course the block is sunk. It's at the bottom of the container. 100% of it is submerged. So what happens now if we make the fluid minimally dense, 0.5 grams per cubic meter? Well, of course, the block is still sunken. And what I'm going to do is I'm going to adjust the block density to 0.2. And according to that equation that we just had, the ratio of the volume which is submerged to the total volume for the object should be equal to the ratio of the density of the object to the density of the fluid. So if I drag this thing up to 0.2 grams per cubic centimeter, the fluid density is 0.5. We should have 0.2 over 0.5. That should give us 0.4. That should mean 40% of this thing is submerged. So let's see what happens. When it comes to rest at equilibrium, sure enough, 40%. And if I increase this block density to 0.4, let's say, then 80% should be submerged. Whoops. There's 0.4. And when it comes to equilibrium, sure enough, 80%. So let's say that I increase the fluid density. Maybe I make it as dense as water. If that's the case, then we should see 40% being submerged. And sure enough, 40% is submerged. If I increase the density to twice water, we should see 20% submerged. Sure enough, 20%. Last but not least, if I go to 2.5 times as much as water, then we expect to see maybe about 8% of this block submerged. So 2.5, 16%. 8% would be if we made this a volume of a density of 0.2 grams per cubic centimeter. And sure enough, there's 8%. So we see that this ratio works, at least according to the simulation that's been put together for us. So I wanted to talk about a couple simple applications of Archimedes' principle. The first one is basically hot air balloons. And what we see here in this picture is the hot air balloon festival that is in Albuquerque. It's an enormous festival. I mean, you can see how many hot air balloons there are. There's usually hundreds, if not more. And basically, how a hot air balloon works is that there's usually some sort of a little basket where the passengers ride. There's a balloon that's filled with air, and then there's usually a little flame that you can use from the basket that heats the air inside of this balloon. And what happens is that when this air is heated, the pressure of the air increases, and basically some air sort of escapes from the little lips below the balloon. And so the air inside this balloon is less dense than all the air surrounding it, and hence the buoyant force upward is greater than the weight downward, and the whole thing gets lifted. And then when you want to descend, you basically allow the air to cool, and by cooling, the air starts to contract a bit, and so more air gets pulled in, and so the pressure equalizes the pressure outside, but now you also have an extra mass attached at the bottom. You have the mass of the fabric and so on. The whole thing ends up being collectively more dense than the surrounding air, and so it starts to descend. So I was thinking about how is it that a pilot actually controls the direction in which the hot air balloon moves. Now, in theory, the way that you can do it is as follows. The air surrounding the hot air balloon does not necessarily have currents which are all in the same uniform direction. Some of the currents may be to the east, and then if you move down just a little bit, some might be north. Then you move down a little more, and they may be south or west or etc. So in theory, the way that you could control where a hot air balloon goes is that you'd either heat it or cool it so that it enters into the part of the air that happens to be traveling in the direction that you want it to be traveling in. Now, there's a few subtleties here. For one, how is it that you know where to put the balloon based on where the air is moving? Well, the answer is that you can have a little pilot balloon that sticks up above and maybe a little weight that sticks below, like a plumb line that sticks below, and you can just watch how both are deflected by the air and see which set of air is going in the direction that you actually want it to move in. Maybe you have a plumb line with multiple weights and maybe a guide balloon of helium with multiple strings and additional balloons attached so that you can see deflections in multiple directions. That's pretty complex sounding already. It actually gets more complex. I have an acquaintance who is involved, at least somewhat involved, and has ridden in hot air balloons a number of times at the Hot Air Balloon Festival that's in Decatur in Alabama. And she informed me that it's usually much more difficult to steer than this because of a few things. For one, they often don't end up bringing along the pilot balloon and the plumb line, or when they do, it tends to be a single pilot balloon that they let go up or bring the slack in. So they're raising or lowering the pilot balloon with respect to the main, and they're raising or lowering the plumb line with respect to the main. But for another, these air currents may shift on you all of a sudden. They're not necessarily steady at one given level. And beyond that, not only are they not necessarily steady, they may not all be in the same direction as they sort of change the level on the balloon. So in other words, the balloon takes up quite a bit of space here. At the bottom of the balloon, you may have a current going this way, and at the top, you may have a current going this way. In other words, you can have shear currents. Usually they're not shear in this sense, but they may be in kind of random collective directions, and you get kind of an average direction that the balloon drifts in. So you can steer the balloon in theory by changing altitude, but in practice it tends to be a little more difficult than that. Second application of Archimedes' principle is found in submarines. And the question is, how is it that you make a submarine surface or submerge? And the answer is you use ballasts. And basically the ballast is sort of a chamber that can surround the submarine, as in this picture, or it can be sort of running parallel to the walls or what have you. And it's a chamber that you can either pump water into or you can pump air into. And when you pump the water into it, then the collective density of the submarine is greater than the density of the water that's surrounding it, and so it starts sinking. And then if you decide that you want to surface the submarine, then you basically pump the water back out of the ballast and it refills with air. There's usually like a tank that you pump the air in or out of, and then you can pump the air back into the ballast or mechanically pump the water out of the ballast and then allow it to refill with air, etc. And when this is filled with air instead of water, then the density of the submarine as a whole is actually less dense than the surrounding water, and so it floats. So that's how submarines are able to float or submerge, or surface or submerge. And of course, again, it can get a little more complicated because you can hit, for example, a pocket of fresh water in which the density is lower than the salt water. And so you might be floating along neutrally buoyant with the salt water, and then you hit this pocket of fresh water and all of a sudden the submarine starts sinking. The third and final simple application of Archimedes' principle that I wanted to address is sort of a more biological example, and that's how is it that a fish is able to duplicate the same thing that the submarine is doing. And so the submarine has ballast, the fish has an organic ballast, a sort of internal ballast that's called a swim bladder. And the fish actually does the same thing as the submarine does, in that it can fill the swim bladder with water, or it can squeeze the water out and fill with air instead. And that actually allows the fish to either float or sink in the water without having to expend too much effort by physically swimming with its tail and its fins. So it just changes its buoyancy, and in fact a fish can therefore float in water at a given level and sort of fall asleep there if it wants to. but return to our feature presentation. What I wanted to talk about next is Pascal's principle. And Pascal's principle basically states that if you apply some pressure to the outside of a fluid, basically you apply an external pressure onto a fluid that is confined, then everywhere inside of the fluid, the local pressure must increase by the amount of pressure that you just applied to that fluid. So one consequence of this, of course, is that if you go deep under the ocean, then everywhere the pressure at the same depth must be whatever the pressure is due to the depth of the water plus the pressure due to the atmosphere that is outside the water that is applying pressure to the water. Another use of it, of course, is in any kind of hydraulic system. Basically, a hydraulic system might look something like this diagram, in which you have a container of water that is enclosed, has a little tube that attaches to a second container of water. The first container has a very small area on top. There's a piston usually placed on top of it. And then the other container also has a larger area and a larger piston placed on top of it. And if you apply a force to the first piston, you therefore are applying some pressure. That pressure increases everywhere inside the fluid, which results in a large force upward because the pressure here is applied over a much larger area. And so you end up getting a mechanical advantage from this hydraulic system. So, of course, some applications would include things such as a hydraulic system used to jack up a car at a mechanic shop. You basically apply some pressure onto a little foot pedal that's equal to whatever amount of force you put for your foot. Maybe it's half of your weight or something, usually actually a lot less. And that's applied to a very small area, and then that goes over a fluid, applies to a large piston, which is placed underneath the car, and therefore a much larger force is applied outward, enough in fact to lift the car. Specifically, you can see that the mechanical advantage is given by the output piston area divided by the input piston area. And so the force out is going to be the output area divided by the input area times whatever force you apply inward. A similar concept is in use in such systems as like a hydraulic brake, by the way. You apply some small pressure here to a pedal that applies a force onto a piston, and then that force gets applied onto some brake pads via a couple of pistons from this fluid. Let's look at a couple examples of that. Suppose that a mechanic is going to actually attempt to lift a car using one of these hydraulic pressures. And so the mechanic puts 100 newtons onto the hydraulic pedal. That pedal is attached to a piston 300 centimeters squared. The car is sitting on a lift with a 10 meters squared piston. So the question is, how heavy of a car can this system lift? All right, to solve this question, we basically just use that the output force, which is equal to the weight of the car, should be equal to the input force times the output area over the input area. So the output area, of course, was given in meters squared, the input in centimeters squared. So we'll say 10.0 meters squared divided by 300 centimeters squared times 1 meter per 100 centimeters quantity squared. So what this means is that the total weight of the car, which may be lifted by this, is about 33,333.3 repeating newtons, or since we're using maybe 3 significant figures, maybe we should write this as about 33,300 newtons. So that is the maximum car weight that can be lifted by this. To give some sense of scale, that would be equivalent to 3,400-ish kilograms, and so that would be maybe a car of weight up to about 7,600 pounds. So, you know, any standard car, SUV, most pickup trucks, etc., are going to be fine on this hydraulic lift. The only note here to add is that this is assuming that the material surrounding the fluid is not broken by the pressure applied by the fluid. In other words, you have to have also a material that you construct the hydraulic system out of that can withstand this much stress. Happily, because this is only a very small force, it's actually going to be probably a very small pressure increase. Specifically, the pressure increase, if you wanted to find it, delta P, would be 100 newtons divided by 300 centimeters squared times 1 meter per 100 centimeters quantity squared. And so this right here would basically be ultimately about 3,333 newtons per meter squared. So delta P, call it 3,330 pascals, is actually a very minor amount of increase in pressure, all things considered. Given that, say, an atmosphere's pressure is 101,000 pascals, we're talking like 3% of an atmosphere, and that's only, you know, far less than a pound per square inch, for example. All right, our other example has to do with hydraulic brakes. So suppose that the piston of your hydraulic brake has a 3 centimeter radius, and suppose that when you slam on the brakes, you can muster 650 newtons of force that's being applied to the brake pads from a cylinder of radius 9 centimeters. So how much pressure do you need to apply to this cylinder in order to have that happen, and consequently how much force do you need to apply? Let's assume that this is 650 newtons total. So that means that you only need 325 newtons per pad. So each pad then has this radius. And so basically the increase in pressure must be the force applied to the pad divided by the area of the pad. So pad. And that's going to be force applied to the pad divided by pi times r squared. So this would be 325 newtons divided by pi times the radius, of course, is 9.0 centimeters, which we can convert to 0.090 meters. And then that is being squared. So the pressure that's being applied has to be given this force divided by this area, which gives us about 12,800 pascals. So how much force do we have to apply to this piston with this radius in order for that to happen? Well, we could recalculate all of this, or we could use the mechanical advantage, which means that Fn needs to be F out times area in over area out. And that's going to be radius squared in over radius squared for out times the force out. This right here is force out. So this is F out. F in, therefore, can be given by 3.0 centimeters over 9.0 centimeters quantity squared times 325 newtons. And so the input force is going to need to be 325 divided by, 3 over 9 is 1/3. We're squaring that, so divided by 9. And that means that we need to put 36.1 newtons of force onto the brake pad in order for this to happen, or excuse me, onto the brake pedal in order for this to happen. Very often when we're measuring pressure, we use some sort of a gauge. And that gauge is usually meant to measure something like blood pressure or tire pressure, hydraulic pressure, etc., with respect to the atmosphere. And so one end of the gauge is often actually open to atmosphere, which means that if the other end is open to atmosphere, the gauge will typically read about 0 when placed in open air. That doesn't necessarily mean that there is 0 pressure on the gauge. Rather, it means that the gauge is ignoring the atmospheric pressure. And so gauge pressure, which is being measured by a gauge, is usually given by some function, be it in a case of a manometer like this one, then it's going to be rho times g times h, where rho is the density of the fluid used, g is free fall acceleration, and h is how much the fluid level rises on the end of open atmosphere with respect to the one that's attached to the thing whose pressure is actually being read. And the absolute pressure, therefore, meaning the absolute pressure of the thing whose pressure is being read by the gauge, is actually going to be whatever the gauge pressure is plus whatever the atmosphere pressure is. So in the case of this object here, the manometer is reading some pressure. For example, maybe this height is 10 centimeters. So it'd be 10 centimeters times whatever the density of this fluid is. Maybe it's water, maybe it's mercury, times the free fall acceleration. Well, that's the gauge pressure. If you want to find out the actual pressure inside of this object, it's that pressure plus 1 atmosphere, or 101,000 pascals. Similarly, this gauge is reading a negative pressure because the end that's open to atmosphere actually has fluid lower than the end that's closed to atmosphere. And so these are vacuum-packed peanuts. The gauge pressure is negative, but the absolute pressure inside of this thing is actually still positive because the atmospheric pressure is greater than the magnitude of the gauge pressure. And so you'd have 1 atmosphere minus h times rho times g. So I've included here a little table which shows some conversion factors for different pressure readings. For example, I keep saying that an atmosphere is 101,000 pascals. Here's a little more detail. It's 101,300 pascals. Sometimes we use bars. A dyne per centimeter squared is what you get if you want to measure everything in grams and centimeters and seconds rather than kilograms and meters and seconds. Torr, millimeters of mercury, atmospheres. All of those are shown here in this conversion table. Of course, the SI unit again is pascals, which is the equivalent to a Newton per meter squared. Let's look at a couple examples of gauge and absolute pressure. So this right here is a standard spring-based tire gauge. It's a simple device. You stick one end over the little cap on your tire. There's going to be some pressure from the tire as a result. It's going to press against a spring, which will basically bring out the little gauge reading that you read, and so you can read off how many pounds per square inch. And so the gauge reads 31 psi. We want to know what the absolute pressure of the tire is. So of course the absolute pressure is going to be the gauge pressure plus the atmospheric pressure. So what is the atmospheric pressure in PSI? Well, that's where this table comes in. So 1 atmosphere is 14.7 pounds per square inch, so 14.7 psi. So our absolute pressure is going to be given by 31 psi plus 14.7 psi. So that means that our absolute pressure is going to be, recall that since this is to the nearest 1, we're going to ultimately round to the nearest 1. So we have 31 plus 14.7, which is 45.7, and that rounds to 46 psi. So the absolute pressure of that tire is 46 psi. Okay, second question, how deep can a scuba tank go if the pressure reads 10 atmospheres? Okay, again, this means that we have P gauge equals 10 atmospheres, or 1,000,000 and 10,000, or excuse me, 13,000 pascals. So how deep can this go? Well, the rule of thumb version is, recall that for every 10 meters depth, you lose or you gain 1 atmosphere of outside pressure. So for every delta H equals 10 meters, delta P equals 1 atmosphere. So we already have 1 atmosphere above the water. So the gauge reading is basically the reading that is equivalent to how much outside pressure do you have when you're sitting at surface. So this is, if you have 10 atmospheres gauge reading, then you can add 10 atmospheres worth of pressure from the water outside of the tank before the water pressure becomes great enough that if you were to puncture the tank, water would rush in rather than air rushing out. So according to this, if you go 10 meters, you gain an atmosphere, and you have 10 atmospheres to go, you can go 10 times 100, which is basically, 10 meters times 10 atmospheres, which is 100 meters. So you can only go, according to this, to a depth of about 100 meters. We can be a little more precise if we'd like. Let's say it's salt water. Then delta P is rho G delta H, and delta P is 1,013,000 pascals as above. So delta H is going to be delta P over rho G, and so that's 1,013,000 pascals divided by 1.025 times 10 to the 3 kilogram per meter cubed times 9.80 meters per second squared. So this gives us a total depth of actually 100.84. But of course we have to round off to 2 significant figures, so that would be 100 meters. And so to offend the level of certainty that we have, the rule of thumb method works just as well as the more rigorous calculation method. In both cases, you can dive to 100 meters before you're deep enough that if you were to puncture the tank, water would start rushing into the tank. This brings me to the last topic that I wanted to discuss in fluid statics, which is surface tension. And basically, the point of surface tension is that the surface of a liquid which is at rest can behave a lot like a membrane which is under tension. And so basically molecules which are in the surface of the liquid are going to be attracted to each other. Molecules that are below the surface are attracted to each other. This is sometimes called cohesion, by the way. So basically what this means is that they will try to pull into the smallest possible area. smallest possible surface area. And if you have a molecule which is at the surface, it's being pulled inward by tension, but there's no molecule above it, for example, to pull outward, or beyond it to pull outward. And so there's a net inward tension force. Now, if you're below the surface, then there is no net tension force, because a molecule above and a molecule below will exert the same force from cohesion. One to the left, one to the right will exert the same force from cohesion, etc. So only at the surface is there an apparent inward tension on the molecule. And so if you put some weight on the surface, it can kind of stretch the liquid a little bit, and thereby increasing its surface area. And that increase in the surface area is then resisted by surface tension. So you have a weight that's trying to make the area larger. You have cohesion, which results in surface tension, which is trying to make the area smaller. And so the end result is that you can end up having a tension force from the liquid which acts upon the object which is placed at the surface. And so there's weight downward, there's two tension forces, one to the left and one to the right, as seen in this diagram, which add up into a net tension force. And sometimes that net tension force will be equal to the weight of the object upon which the tension is placed, and so the object appears to float entirely, 0% submerged, as opposed to a buoyant force in which the thing would just be simply floating. So that's basically how, for example, those water strider bugs are able to walk across the water, the surface of water. And there's a few ways that you can measure surface tension. One is that you can measure the size of a drop which is formed from a simple pipette. If you were to measure the diameter of the pipette, then you have the effective length along which the water drop is going to be, or drop of whatever liquid is in contact with the pipette. And so that gives you the surface tension upward. The volume times the density gives you the mass. Basically, if you know what the length is, the surface tension is usually given by force divided by length. So if you know what the diameter is, you know what the circumference is, that's your length term. You know what the weight is, that's your force term. And so the surface tension is the ratio of those two. Basically, you can do something like counting how many drops out of the end of the pipette it takes before you have filled up a graduated cylinder, for example. So how many drops is in 100 milliliters, and that tells you what the volume of a drop is, and if you know what the density is, then you've got the weight. The other way to do it is to use a loop, kind of like this one that's pictured in this diagram. And so basically, you dip the loop in water or whatever it is that you're trying to measure the surface tension of, and you can grab one end of this loop and basically move it along these wires. And so that stretches the fluid like a membrane. And so how much force do you need in order to pull the loop and thus stretch the film's surface? And the answer is that force should be equal to whatever is the length of this loop times whatever is the surface tension. And then usually there's a factor of 2, because you have a surface tension above and you have a surface tension below. There's 2 surfaces for the membrane, a top surface and a bottom surface. So here I've included a list of common fluids, common liquids really, and what their surface tensions are. So let's look at a couple examples. Suppose you have a loop of some length. We want to know how much force do you need to pull the loop if there's water in the loop. So looking at this table, Depends upon the temperature of the water. Let's assume we're at room temperature. So the surface tension is 0.0728 newtons per meter. So we use basically that the force is the surface tension times the length, and in this case the length is twice the length of the loop. Length of the loop is given here as 2.0 centimeters, so L equals 2.0 centimeters is the same as 0.020 meters. So the force needed is going to be 0.0728 Newton per meter times 0.020 meters. And so what that gives us is a total force of 0.002912. So the force is about 0.0029 newtons. So that's how much force you'd need to pull with in order to pull the loop along. Again, assuming that the loop is on a frictionless track. Okay, so the other question is, suppose you've got a certain bug. It's got 6 legs. Each one has a spherical cross-section of a given diameter, and it's going to have surface tension acting at an angle of 60 degrees on each of the legs. So we want to know what the mass of the bug must be based on that. Okay, so free body diagram first of all. The length over which this is being acting is, here is our diameter, and this is 41.0 microns of diameter. And so the length here, 41.0 microns times pi. And we might want to convert this into meters. So length is basically going to be, let's do 41 times pi. And 41 was micrometers, so this gives us 129 basically. So this becomes 1.29 times 10 to the minus 4 meters. Because again, this right here is going to give us about 129 micrometers. 1 micrometer is equivalent to 1 times 10 to the minus 6 meters. So this is the length of each leg. The total length L is 6 times this length because each of these is 1/6 of the total leg number. In other words, the bug's got 6 legs. So what this ends up giving when you multiply everything together is about 773 microns. Obviously I have a couple more digits in my calculator than is shown here. And so this is length equals 7.73 times 10 to the minus 4 meters. Okay, so that's the length. Now, the force should be the mass of the bug times the free fall acceleration, and that should also equal the surface tension times the total length. So the mass should be, now we got to be careful here. We can't just say surface tension times length. We're going to call this surface tension times length times this factor at which the surface tension is acting. This factor is that the surface tension is acting on an angle of 60 degrees on each of the bug's legs. So the surface tension itself is not all acting entirely upward. In other words, we need to, if we were going to draw it from the side, the surface tension is acting like this, and this angle here is 60 degrees, and we need to have the vertical component. So this would be 30 degrees. Vertical component goes with sine of the angle. So we're basically going to go times sine of 30. So the mass should be gamma times L times the sine of 30 divided by the free fall acceleration. So 0.0728 Newton per meter was the surface tension for water, times the total length, which was 7.73 times 10 to the minus 4 meters, times the sine of 30 divided by 9.80 meters per second squared. And so the mass of the bug, according to this, is going to be about 2.87 times 10 to the minus 6 kilograms. So that's, in other words, a mass of 2.87 milligrams, however you want to slice it. So is this a reasonable seeming mass? Well, this is basically about, of order 1 times 10 to the minus 5 kilograms. It's the same general order of magnitude. I bring that up because a common table included in many physics textbooks is one that gives approximate order of magnitude masses of a variety of things. And the one that I'm specifically interested in here is that this one gives the mass order of magnitude of a bug, and it's 1 times 10 to the minus 5, which would be equivalent in this scale to 10 milligrams. So the order of magnitude estimate from this book and the rough estimate we got from this calculation show that this is in fact a fairly reasonable estimate for the mass of this water skiing bug. Granted, though, a mosquito is usually a bit smaller than one of these water strider bugs, so take it with a grain of salt. So there you have it. That is fluid statics in a nutshell. There's quite a bit of information in this lecture, I suppose, but a lot of it goes back to the same couple principles, really, if you want to include the surface tension as a separate principle. The two basic principles in here would be basically Archimedes Principle and then also the surface tension principle. A third one that's also pretty important is how to figure out how much weight of water has been displaced, or in other words, how to figure out the pressure differential between top of the water and bottom of the water. Although, as it turns out, that is basically a special application of Newton's second law, or of Newton's first law, really both together, in finding the weight of a column of water of a given area and then figuring out how much force is needed in order to support that column of water. So that's all I've got for today, and I hope you found this video helpful, and thank you for